It's so central to life that we don't often give it a second thought. But how light gets from there to here turns out to be an incredible story. The energy created in the fusion process is carried out of the core by particles of light and heat called photons. They are what bring the warming rays of the sun to Earth. To reach our planet, these glowing travelers from our nearest star must first take a long, winding road through all the layers of the sun, like Dante journeying through the levels of hell. First, a photon enters the 185,000-mile thick radiative zone. The region is so densely packed that the photon constantly bumps into other particles, like hydrogen and helium atoms. It struggles outward in a chaotic zigzag pattern that scientists call the random walk.
A photon can't escape without interacting over and over and over and over again, getting absorbed by atoms and re-emitted, and it can be absorbed and re-emitted millions of times. As the density decreases, as you get further up in the sun, it becomes easier, and the collisions and the interactions are less.
When it finally reaches to within 130,000 miles of the surface, the photon enters the convective zone, and the pace suddenly quickens. It's carried upwards by a kind of boiling, riding along in huge columns of gas at hundreds of miles an hour, taking only 10 days to emerge on the solar surface. The incredible journey is almost over as the photon lifts off through the wispy gases of the solar atmosphere. From there, it takes only 8 minutes for it to zip across 93 million miles of space to our planet. Incredibly, by the time sunlight actually reaches Earth, it's already been in existence for hundreds of thousands, if not millions, of years. For the sun, even a million years is a small blip in time. The simple, perfect disk of a sunset belies the long, violent history of our star. It is a ball of fire spawned billions of years ago in a massive explosion known as a supernova.
After this titanic explosion, where a star much larger than the sun exploded, there would have been a huge cloud of gas, many times larger than the solar system. And small knots of material would have gradually coalesced in this very large cloud.
About 5 billion years ago, some 10 billion years after the Big Bang that scientists believe kick-started our universe, this cloud started to collapse under the pull of gravity.
Our solar system probably arose from one such knot of self-gravitating gas that pulled itself together and gradually spun itself up as it pulled in, like a skater pulling her arms in during a spin, until the star and the various planets coalesced around it. Ultimately, when the star was dense enough, it would have turned on fusion and started glowing, giving off sunlight.
Why do scientists believe the sun was born from the ashes of a supernova? The evidence lies beneath our feet. Complex, heavy elements like the uranium we mine from the Earth to fuel our nuclear power plants could not have been forged in the sun. There is simply not enough heat in a star that size to create elements any heavier than iron. Heavy elements like uranium can only be created in a catastrophic cosmic explosion. Earth and the other planets in the solar system formed out of the same knot of gas that produced the sun. In this process, the sun hoarded 99% of the mass. This means it's the biggest object in our celestial neighborhood with the strongest gravitational pull. That's why everything else revolves around it. Of all the planets, Earth earned a privileged place in relation to the sun. If we were closer in, our oceans would boil away and the ground would be hot enough to melt lead. If we were farther out, our planet would be a frozen wasteland.
Sort of like Goldilocks and the Three Bears. Not too hot, not too cold, it's just right. Here we are at about 93 million miles away from the sun, and we're happy to be here. We're lucky to be here. And In some sense, we're here because it's the right circumstance for us to be here.
Earth may be in just the right place in the solar system, but we're also close enough to the sun to be a target of its fury. Thousands of mammoth explosions rock our sun every year. You might expect this explosive force to come from nuclear reactions in the core. But in reality, what drives all outbursts of solar violence is magnetism. Since Earth rotates as a solid, our magnetic field is simple. We have two poles, north and south. This is what makes a compass so useful for finding your way around the planet. But imagine if instead of two poles, you had 1 to 10 million. This is what happens on the sun. The sun's magnetic field is a tangled web because even though it's held together by gravity, the plasma doesn't rotate evenly. Plasma at the equator rotates once every 25 Earth days, while plasma at the poles takes roughly 35 days to circle once.
The sun has what we call differential rotation. You have all of this plasma that is really turning and churning, and that causes magnetic field lines to become twisted and intertwined and mixed up.
Although magnetic field lines are invisible, we know they exist on the sun by looking at features called coronal loops and prominences rising up into the solar atmosphere. Just as metal shavings line up in the presence of a simple magnet, these loops of plasma perfectly outline the magnetic structures that support them from below. These plasma arches are so tall and wide that you could slide a planet as big as Jupiter right through them. Sometimes magnetic fields can twist plasma in the sun's atmosphere into majestic helical shapes called flux ropes.
Magnetic flux rope is sort of like a slinky. The magnetic